Welcome to today's Explainer. Whether you're a university student tackling thermal systems for the first time or a lecturer looking for a solid breakdown for your class, you are absolutely in the right place. Today we're diving into the thermodynamics of reacting mixtures. We're going to take a really structured journey from the basic chemistry of burning fuel all the way up to advanced exergy analysis. By the end of this, you'll have a crystal clear grasp of the math and the thermodynamic principles we actually use to figure out the true potential of the energy we consume.
Okay, here is our roadmap for today. 1. Fundamentals of fuel. 2. Modeling combustion reactions. 3. Energy and heating values. 4. Adiabatic flame temperature. And 5. Understanding chemical exergy. Let's get into it.
Section 1. Fundamentals of fuel. Defining the source of power.
Right, so before we get lost in the complex math of thermodynamics, we need to establish our starting point. Every single thermodynamic model starts with the fuel. Now, theoretically, an ideal fuel is readily available, it's cheap, it burns easily, and it gives off a massive amount of heat. Oh, and it should be easy to transport with zero harmful byproducts. But, as any engineering student knows, the real world is all about compromise. Actually burning these fuels almost always produces emissions, and that carries real environmental weight, like air pollution and greenhouse gases. So we're constantly playing this balancing act between getting high heat release and keeping our environmental impact in check.
And the physical reality of these fuels directly changes how we model them. Take a look here. On one side, we've got fossil fuels: coal, crude oil, natural gas. These took literally millions of years to form, locking incredible energy density inside these complex hydrocarbon chains. On the flip side, we have the biofuel cycle. These come from recently living organisms, think plant oils or even recycled cooking grease. Grounding our math in these actual physical materials is super important because the specific chemical makeup of your source completely alters the stoichiometric requirements of your entire system.
Section 2. Modeling combustion reactions, the chemistry of burning.
So, transitioning from the physical fuel to the actual chemical reality of burning it, we've got to distinguish between complete and incomplete combustion. Complete combustion is the dream. It's our theoretical ideal, where every bit of carbon burns perfectly into carbon dioxide, all the hydrogen turns into water, and any sulfur becomes sulfur dioxide. Everything is fully oxidized. But, well, that rarely happens. In practical engineering applications, we almost always see incomplete combustion, which leaves behind unburned carbon, carbon monoxide, and a bunch of other intermediate stuff. To mathematically model that perfect theoretical ideal, we use equations like this one. This shows the complete combustion of methane, or CH4, using theoretical air. Now, in most real setups, air is what's supplying our oxygen. For engineering simplicity, we use a model of dry air. We literally just treat it as exactly 21% oxygen and 79% nitrogen. Because of that fixed ratio, every single mole of oxygen drags along exactly 3.76 moles of nitrogen with it. You just divide 0.79 by 0.21 to get that number. So in this balanced equation, that coefficient of 2 right in front of the oxygen-nitrogen mix, that dictates the exact theoretical amount of air you need to fully oxidize the methane, while all that nitrogen just passes through completely unreacted.
But what happens when we tweak the parameters? Say we supply 150% theoretical air. Now we're pumping in 1.5 times the required amount. And honestly, supplying excess air is a super common engineering trick. It ensures we get complete oxidation and helps us control the temperatures inside the combustion chamber. But notice how the product mix changes on the right side of the equation. Because we dumped in excess air, it shows up in the products as unburned oxygen, plus a way bigger chunk of nitrogen, 11.28 moles to be exact. The original fuel hasn't changed at all, but the actual thermodynamic mass leaving the system has shifted completely.
And because real-world combustion is usually messy and incomplete, we can't just rely on theoretical equations on a whiteboard. We have to measure the actual combustion products directly. A lot of exhaust sensors will give you what's called a dry product analysis. All this means is that they're giving you the mole fractions for everything coming out of the exhaust except the water. This gives engineers a hard empirical baseline. You take those numbers, work backward, and figure out the exact chemical reaction that just happened inside a running engine.
Section 3. Energy and heating values, measuring released heat.
All right, so to actually quantify the thermal energy released during these reactions, we look at heating values. When fuel oxidizes quickly, it releases energy, and we break that energy down into two main metrics. First is the higher heating value, or HHV. We use this when we assume all the water created by the combustion condenses completely back into a liquid. Then there's the lower heating value, or LHV, which assumes all that water stays as a vapor.
The higher heating value is always going to be bigger than the lower heating value, and the difference between them is exactly the latent heat of vaporization. It's literally the energy you'd get back if all that hot steam condensed into liquid water.
Let's look at how this plays out with real-world data at standard reference states, so 298 Kelvin and 1 atmosphere. The contrasts are pretty stark. If we compare liquid octane, which is basically our model for standard gasoline, with liquid ethanol, a common biofuel, you can immediately see why our system designs have to adapt. Octane has a lower heating value of 44,430 kilojoules per kilogram. Ethanol? It drops way down to 26,800. Gaseous methane, though, jumps up to over 50,000 kilojoules per kilogram. These aren't just trivia facts. These numbers dictate the physical realities we just talked about. They're absolutely crucial for figuring out the required fuel flow rates and the overall efficiency of your thermal systems.
Section 4. Adiabatic flame temperature. Visualizing the heat.
Moving from those static heating numbers to a dynamic running system, let's establish the parameters for a steady-state combustion reactor. If we assume there's no work being done, and we ignore kinetic and potential energy, the energy released by our burning fuel can only leave this reactor in two ways. It either exits with the hot combustion products, or it's lost as heat transfer to the surroundings. The adiabatic flame temperature is the absolute theoretical maximum temperature those exhaust products could reach if we perfectly insulated the reactor, meaning zero heat escapes. Every single drop of liberated energy goes straight into heating up those gases.
Now when we run an energy rate balance and start playing with the percentage of theoretical air, a really clear inverse relationship pops up. As you increase the theoretical air from 100% up to 400%, the adiabatic flame temperature absolutely plummets. And the physics behind it is pretty straightforward. All that excess air, specifically the extra nitrogen and unburned oxygen we looked at earlier, acts like a giant thermal sponge. It just soaks up a massive portion of the liberated heat, dragging the overall temperature of the combustion products right down.
Section 5. Understanding chemical exergy, the true value fuel.
Okay, so moving beyond just calculating basic thermal energy, we have to ask how much of that energy is actually useful to us. This quote from the source material is perfect for bringing a highly abstract concept right back down to earth. When you fill an automobile's fuel tank with gasoline, it is the exergy of the gasoline you seek and for which you pay. Think about it. A warm cloud of exhaust gas has energy, for sure, but you can't use it to turn a drive shaft. Exergy is the property that measures the actual potential for useful work. It is the real economic and mechanical value we're trying to extract. It's so important in thermodynamics to realize that exergy is not just another word for energy. They are totally different things. Thanks to the first law of thermodynamics, energy is always conserved. It just changes forms, right? From chemical bonds to sensible heat. But exergy? Exergy gets destroyed. As your fuel burns and goes from this highly organized, useful state into a messy, dispersed cloud of warm exhaust, its potential to do work disappears. That potential is destroyed mainly because the combustion process itself is fundamentally irreversible. Technically speaking, exergy is defined as the maximum theoretical work you can get as a system reaches equilibrium with the environment. But what environment are we talking about? Well, in thermodynamics, we define a specific exergy reference environment. It's basically a standardized mathematical model for the Earth and its atmosphere. If your system is at a different temperature or pressure than this baseline, it has thermomechanical exergy. But there's also chemical exergy. And chemical exergy exists purely because there is a difference in chemical composition between our highly ordered fuel and that standard background environment.
When we calculate the exact standard molar chemical exergy for substances like methane or octane, we're finding the absolute maximum theoretical work hidden inside them, based entirely on how different they are from the Earth's atmosphere. Finding these exact baseline numbers gives us the ultimate theoretical ceiling for power generation. It lets engineers precisely quantify how much thermodynamic potential is being wasted in a system, and it gives them a clear target to aim for when they're designing better combustion chambers or power cycles.
Which brings us to our final takeaway. Exergy analysis isn't just some dry academic exercise. It's a real-world tool that's absolutely crucial for maximizing both our non-renewable and renewable energy resources. By identifying exactly where and how potential work is destroyed during combustion, we're faced with a really important question. How will applying exergy analysis change the way we design the thermal systems of tomorrow? Honestly, it's up to the students, researchers, and lecturers out there to use these thermodynamic models to build our future engineering solutions. Thank you so much for joining me for this explainer on reacting mixtures, and keep analyzing that potential.